Today's lesson is talking about the second derivative test. The second derivative test is another method for finding relative extrema. Previously, you learned how to find relative extrema using the first derivative test, so the second derivative test is just another option for finding the relative extrema. The AP standards for today say the second derivative of a function may determine whether a critical point is the location of a relative maximum or minimum. There's a key word there, may. So we'll see in a minute that this doesn't always work. The second one says when a continuous function has only one critical point on an interval on its domain, and the critical point corresponds to a relative extrema of the function on the interval, then that critical point also corresponds to the absolute extremum of the function on the interval. We won't specifically look at this one today. But just know that that standard is connected to what we're doing today. When we used the first derivative test last week, we were using horizontal or vertical tangents to try to find the relative extrema. If we had a horizontal tangent, that means that the derivative was equal to 0 at that point. If it was a vertical tangent, that means that the derivative was undefined at that point. So the derivative did not exist. As we'll see in a minute, the second derivative test is very similar to the first derivative test. Where it differs is that it uses concavity to help find relative extrema. In the first derivative test, we found the critical points and then did a sign test around those critical points to test whether the derivative was positive or negative. When we use the second derivative test today, we'll see that there is no sign test. Let's start with a quick review of some concepts we've learned about derivatives so far. Earlier in this unit, we learned about concavity, and the word concave means that the graph is curving upwards. And we found that f double prime of x was greater than 0. That is, if f double prime was positive, that meant that f of x was concave. We also learned about convex, aka concave down, and that if f double prime of x was less than 0, or if f double prime of x was negative, that meant that your graph of f was convex. Earlier in the semester, we learned that f of x has a horizontal tangent whenever f prime of x is equal to 0. And we used that fact whenever we were doing the first derivative test. We'll also use this fact today when we're doing the second derivative test. And finally, we learned earlier in the semester that if f of x has a vertical tangent, that meant that f prime of x does not exist. So now let's look at how the second derivative test works. There are 3 scenarios to consider. The first scenario is whenever you have a local maximum point. If you have a maximum, that means that your graph must be convex. And if your graph is convex, that means that f double prime of x is less than 0. We also know that at a maximum point that you have a horizontal tangent or a vertical tangent. That means that f prime of x is either equal to 0 or does not exist. In this graph that I've drawn here, this represents the scenario when f prime of x is equal to 0, but this also works whenever it does not exist. To use the second derivative test for this first scenario, if you can show that f prime of c is equal to 0, or it fails, and also show that the second derivative of that point is less than 0, that means that f of x has a relative max at x equals c. Scenario 2, you have a local minimum. At a local minimum, your graph must be concave. Which means that f double prime of x would be greater than 0 at that point C. We also know that at a local minimum, that you either have a horizontal tangent, that is, f prime of x is equal to 0, or you can have a vertical tangent, which means that f prime of x does not exist. to use the second derivative test in the second scenario, if you can show that f prime of c is equal to 0 or it fails, and also show that the second derivative at that point c is greater than 0, so it's concave, that means that f of x has to have a relative minimum at that point, x equals c. There's also a third scenario you have to be aware of. If f prime of x is equal to 0 or it fails, and then the second derivative is equal to 0, that means that the second derivative test is inconclusive. At this point, you would have to do the first derivative test to find any local min or maxes. In the next video, we'll see how we can use the second derivative test to find local extrema.